Okay, let us continue with the free particle case in Schrodinger equation. And in the previous lecture, we have stopped at the problem with the normalization of a free particle Schrodinger equation. So, if we have a problem with the normalization, here what we have faced is the normalization integral getting diverged. So one way is to solve this situation is to restrict the domain of the particle, that is a free particle, under investigation to an arbitrarily large length L and to impose a periodic boundary condition at the endpoints. So there are many ways to normalize the free particle wave function. We will be discussing two of such methods here, and the first one is what we are talking about, that is a box normalization. In the box normalization, we are going to confine the particle to a box of length capital L and impose periodic boundary conditions at the endpoints. And the periodic boundary condition is that k is equal to 2 pi n by L, and k is allowed to take the discrete values based on n is equal to 0, plus or minus 1, plus or minus 2, etc. So if we have such a condition, if we are restricting the free particle in a box of length L, I should mention that we are considering a one-dimensional box, since our wave function looked like e raised to plus or minus ikx. So let us analyze it. Yes, this is our Schrodinger equation, and the value of wave function we have chosen is either a e raised to ikx or e raised to minus ikx, or it could be the combination of both. So now in the box normalization, what we are doing is we are going to take a box of length L and say that the free particle is in this box. So I'm free to choose the limit from 0 to L or minus L by 2 to plus L by 2. In both the cases, we can see that the length of one side will be capital L. So the periodic boundary condition is this one, k is equal to 2 pi n by L. Now let us go for the normalization. So in the normalization, we have to give the limit, that is the limit of a box, limit as the side of a box from 0 to L or minus L by 2 to plus L by 2. Here for simplicity, we are choosing 0 to L. And the psi star part is a star e raised to minus ikx, and psi is a e raised to ikx dx is equal to 1. That is a normalization condition. Okay, so as you know, the coefficient a star a is taken as mod a square, and you can see that e raised to ikx and minus ikx get cancelled. That means the integral becomes mod a square integral 0 to L dx is equal to 1. So integral 0 to L dx is x between the limit upper limit L and lower limit 0. Applying the limits, mod a square L minus 0 is equal to 1. That means mod a square is equal to 1 by L, or a is equal to 1 by square root of L. So we can give the constant a, that is 1 by square root of L, what we have obtained just now. So giving that value, we have the wave function 1 by square root of L into e raised to I kx. So in this condition, since we have applied the boundary condition or the periodic boundary condition of a box of length L and obtained the wave function using the normalization constant 1 by square root of L, we say that the free particle is box normalized now. So the free particle is box normalized because we are confining, we are changing the condition in such a way that we confine the particle into a one-dimensional box. Now, in this case, let us analyze how the energy eigenvalues get varied. So this is going to be the eigenfunction. Now, we already have, when we have formulated the Schrodinger equation, we already assigned k square is equal to 2m e by h cut square, and from this e is h cut square by h cut square k square by 2m, and k is taken from the periodic boundary condition k is equal to 2 pi n by L. So k square is equal to 4 pi square n square by L square. Apply it here, apply it in the value of E. So we have 4 pi square n square h cut square by 2ml square. So if we give the values 0, 1, 2, etc., you will get the possible energy values or the energy eigenvalues. So this is how we are box normalizing the free particle and obtaining the wave function, eigenfunction and eigenvalue in the case of box normalization. Now, if the situation is like the wave function behaves like a Dirac delta function, so we can apply a Dirac delta integral that can be, Dirac delta function in order to normalize the wave function. So the significance or importance of Dirac delta function is that, as you can see, if we have a function sin g of x, then limit g tends to infinity, sin g of x divided by pi x gives the value of delta of x. That means the function should to a large value when the variable tends to 0. So delta x peaks to infinity. So that is how Dirac delta function behaves. So in the case of Dirac delta function, we can define delta x as delta of x is equal to 0 when x not equal to 0 and it is equal to infinity when x is equal to 0. And the normalization can be given like this. Integral minus infinity to plus infinity delta of x dx is equal to 1. Okay, so if that is the condition, this is another way of defining the same thing with another more variable introduced like x0. But it is just the condition is same as the previous one I have just explained to you. Now let us see how we are going to apply Dirac delta function for normalizing the free particle wave function. So in order to use this, we are going to rewrite our wave function as a psi k of x. Okay, so psi k of x is actually constant a into e raised to I kx. Okay, so let us derive the normalization condition. Integral minus infinity to plus infinity psi k star psi k prime dx is equal to delta k k prime is equal to 1. So if the variable eigenvalues are discrete values, then we can use the Kronecker delta symbol, that is delta k k prime is equal to 1. If it is a continuous variable, eigenvalues are continuous, then we have to use a Dirac delta function. So delta k prime minus k is equal to 1. So that is how we are defining if the eigenvalues are discrete or continuous. Okay, here we are dealing with the continuous case. So integral minus infinity to plus infinity, coefficient psi star psi is taken. So a star e raised to minus ikx, a e raised to I k prime x dx. That should be equal to Dirac delta function. Okay. So if this one is to satisfy the Dirac delta function, the constant to be chosen such that it is 1 by square root of 2 pi. So if mod a square is 1 by 2 pi or a is 1 by square root of 2 pi, you will get the value of this integral normalization as delta k prime minus k. So the constant can be given and the wave function can be rewritten. So this is how we are normalizing in the case if we have the behavior of the system is like Dirac delta potential. So we expect a maximum value of the function at the middle where the variable x is equal to 0, and it decays very fast, so it looks like a peak. So this is how we are normalizing. These are the two different ways of normalizing free particle wave function. So in both the cases we can obtain the energy eigenfunctions and the eigenvalues. So this is how we are solving free particle Schrodinger equation by selecting either of the modes of normalization, because the wave function we have obtained is not normalizable because it is getting diverged. So in order to avoid that, we have to choose either box normalization or delta function normalization.